I have to say, it's amazing to be here. I was a kid, watching the Christmas lectures growing up, and this is just amazing. It's very much an honor to be here. And I'm hoping to take you through how we know what we know about our own universe, and like Jason said, maybe briefly even beyond it. And I want to start here. So I'm a cosmologist. Cosmologists study the origin, the evolution, and the fate of our universe. Just the small stuff. So for the very longest time, cosmology was a speculative subject. It's one of the oldest branches of science. So you can see here, this is the Flammarion woodcut, a medieval person trying to pierce through the dome of the sky to try to figure out what makes the universe tick, what is behind all of these lights we see in the sky. And cosmologists today are still doing that. It's a different kind of science than all the other experimental sciences where you can actually go and make experiments and try to see directly how the universe works. But I think you'll probably agree it's a good thing that we can't make a universe in the lab. We can't make one pop into existence, poke at it, change a little bit, see what's going on. We can't do that. So we have to become detectives. We have to look for the clues that the universe itself left us. And it seems that nature has been very kind to us. Nature has left us clues that express themselves in the language of mathematics and display themselves to us in the data that we can obtain by looking out into space. And one of the reasons that this is possible is a quirk of nature, which is that light has a speed limit. So, this is a bane of science fiction writers everywhere. Light has a speed limit. It's very fast, but it's finite. So this means that even the nearest stars, when light from the nearest stars reach us, several years have gone by for that light to travel to us, so we see those stars as they were in the past. And this works further and further away as well. As we look out into the depths of space, we see the universe as it was when it was older. And eventually, it starts to look quite different from the modern-day universe. It starts to look simpler, darker. And you can roll back time in this sort of time travel to the very earliest light you can see in the universe. We call this the cosmic microwave background. So I'm going to start our story by rewinding all the way back to 13.8 billion years ago, when this light came into being. It's Super Tuesday today, so let's start with the dawn's ancient light. So, reminding ourselves that we live inside a galaxy. So we live in a spiral arm of a galaxy, and many of the maps of the universe that I'm going to show you in this microwave light is going to look like taking a whole sphere and projecting it into this sort of elliptical projection. So when I show you maps like that, it's going to be the whole sky. So our galaxy looks different as you go to longer and longer wavelengths here. Eventually, you get to the microwave wavelengths. And then you turn up the contrast by a factor of 100,000. And the universe looks like that. So you see this red band across this picture. That's the emission from our own galaxy, gas in our own galaxy, in the microwave bands. But if you look above and below this band, you see these little mottles of blue and green. These tiny patches indicate variations in the temperature of the universe and hence its density at 1 part in 100,000 at a very, very early time. So early that it's a baby picture of the universe. This light comes to us from when the universe was only 380,000 years old. It's the earliest light we can see. And these little patches, these little mottles, actually form the seeds of all of the structure that appears in our universe today. Everything that we see, from a galaxy to a person to planet, somehow came from the fact that the very early universe was very slightly uneven in its density from one place to another. It all grew under the action of gravity into what we have seen today. I'm going to lead you through the history of this light and how we can learn about the universe from it. And I want to start at the beginning with its discovery. So it was discovered in 1964 by these two blokes, so Arno Penzias and Robert Wilson. They were working at Bell Labs in New Jersey. And they built this experimental radio telescope to do something far more mundane. They wanted to look at the radiation from gas in interstellar space between the stars. And they came to find that there was a funny kind of hiss in this instrument. And it was coming from all over the sky. And they thought they got something wrong. There's some noise in the instrument, and they started getting very obsessed with pigeon droppings. They called it, very delicately, a white dielectric subject. And they started getting into the telescope, scooping this stuff out, and eventually they found that that didn't work. I've recently learned that there is an actual murder mystery here. You know, pigeons, they home, so you can take them away, but they come back home. So sadly, the pigeons were shot. And the hiss continued. And the pigeons gave their lives in vain. It is very sad. However, these guys walked down the road to Princeton University and met some of their colleagues who had actually been actively looking for this hiss, this noise in their instrument. And basically, it was the afterglow of the Big Bang. It had been predicted in the 1940s. It was discovered by accident in 1964. The pigeons didn't get anything, but these guys won the Nobel Prize for their trouble. So I'm going to fast forward through a lot of blood, sweat, and tears to 1992. By this time, our instruments had improved enough that we could put a satellite in space to measure this radiation very accurately, the afterglow of the Big Bang. And if you actually look at this satellite, this is called Cosmic Background Explorer, COBE. It made a map like this and showed that this light, this very uniform light all over the sky, was very cold. It was at about 3 degrees above absolute zero. Extremely cold in space. And on top of that, it did something remarkable. So it's great that you see this light coming from everywhere. It's in this room, and it's a very uniform temperature. That tells you the very early universe was very homogeneous. And it doesn't tell you where all the stuff in the universe today, which is very inhomogeneous, where did that come from? So this experiment actually discovered the primordial ripples from which everything came. This is the map they made. It's quite crude. You can see the red band of the galaxy going through it. It's got quite low resolution. But this was it. This was the discovery of the origin of structure in the universe, without which we would not be here. I want to start to show you the human face of some of these experiments as well. So Penzias and Wilson, a couple of people, they built an experiment, they got the Nobel Prize. Now we're starting to see teams of people, and this is a theme that I hope that you will capture as I go on with my talk, about how it takes a cooperation of different people to get to these discoveries. So this is part of the COBE team. I find it very enjoyable to see some of my colleagues in these 80s costumes. There's George Smoot. He's celebrating his Nobel Prize, perhaps, but he also likes life a lot, so maybe this is something else. And this John Mather, who also got the Nobel Prize for this discovery. And I want to show you also the culprit over there. There might be people in the room that don't recognize that that's a computer. Computers. So people have been building brilliant experiments for a long time to try to understand the universe. Computers now increasingly play a fundamental role in it, and you can start to see the appearance of a computer along with the team that they made the discovery. In 2003, we had a second-generation satellite from NASA. This is the Wilkinson Microwave Anisotropy Probe. Try saying that fast several times. So what this satellite did, it was a much bigger increase in sensitivity and resolution from COBE, and that very crude map of the primordial ripples that COBE made came into sharp focus. So this is the map with the help of which we figured out the so-called standard model of cosmology. It's a model that describes basically all of the data that we have obtained about the universe, and I'll get to it in a little bit. I want to show you part of the WMAP team as well. This is personally a very important picture for me because I'm actually there. And that was during my PhD, and you can see us looking very, very happy because that's when that day, we got the first cosmological results from looking at this map. And there's Dave Wilkinson, who the satellite is named after, a brilliant experimentalist. So now I want to actually tell us a little bit about what we are seeing when we see this light. So the early universe was very hot. It was so hot that electrons were separated from their nuclei. Okay, so the whole thing was ionized, it was a plasma. And packets of light, or photons, couldn't get very far because they kept bouncing off all of the free electrons. So the universe was opaque to light. And eventually, as the universe expanded, it cooled. And even though this is still very hot, when it was about 3,000 degrees Kelvin, you could not keep these atoms ionized anymore. It was cold enough for neutral atoms to form. And at that time, this light was released. It was the universe becoming transparent that released the light. And since then, the light has been traveling to us through space. So one of the most remarkable things about these journeys of these photons from this very early time, remember, they were released at 380,000 years after the Big Bang. And they have been traveling to us for over 13 billion years, and during that time, before they were eaten by our detectors, they have mostly never encountered any other matter. The universe is extremely empty. And what you're seeing here is the pristine image of this light. So why is it in the microwave? So in the very early universe, when it was very hot, they were not microwaves, they were gamma rays, X-rays, very, very energetic photons. But as they travel through the universe, it shares in the expansion of the universe. So the wavelength of this light gets stretched out, and they become stretched into the microwave, where we see them now. So it's cooling down, it's stretching, and now we see it in the microwave. And when we're looking at these maps, what you're seeing is a cosmic tug of war, a battle between gravity and pressure, which sets up sound waves in the sea of electrons and photons in the early universe. And you can see these vibrations happening at all of the different scales that we can see in the universe. And at the moment that the universe becomes transparent, you see the sound waves just frozen. So you're hearing the sound of the universe when it was very young. You can actually convert the data that we get from the microwave background into sound and listen to the structure in it. So you can hear that it's not a hiss, it's not uniform, it has structure in it, there's a scale to it. So how can we actually use this data to learn anything about the universe? It's because, in addition to these beautiful instruments that can measure the sky, we also have theories. And these theories make predictions for what the sky should look like. So remember, we can't do experiments. We can make predictions, though, from theories of physics. And we can actually compare what we get out of these theories with the data. So this map is like a fingerprint, and you can identify the culprit theory by comparing a lot of theories with the data and coming up with the one that fits the fingerprint. Here again, the advent of computers is really, really important. So we need to calculate what this fingerprint looks like, and that requires usually a huge amount of supercomputer time to analyze all of this data. And when we do that, what we find is something rather surprising. This map that was made by WMAP is basically 3 megapixels. So you know how much information there is in all of those pixels. All of that information in that map is basically described by 6 numbers. So these numbers tell us things like, when did the first stars form? How much atomic or baryonic matter is there in the universe? How much dark matter is there in the universe? What is the shape or geometry of the universe? How old is it? And how clumpy was this very early universe? So these 6 things can describe all of this data. That is, first of all, really surprising because it's simple. However, it tells us already 3 things that we don't think that we expected, which is that there's dark matter, there's dark energy, and the early universe was clumpy, so something made all of the structure in the early universe. Those 3 ingredients are not in our standard theories of physics. It's already telling us that there's a lot we don't know. It's simple, and yet it's bizarre and strange. So before we go on, I'm going to now rewind this story that we have learned about the universe and show you the history as we understand it following WMAP. So we're going to go into a cold spot. It's an overdensity, so there's extra gravity there, extra mass there, and it attracts other matter towards that. The early universe is dark, but then eventually the first stars turn on. And they light up the universe with their UV light. And eventually, all of these structures form along filaments of dark matter, and you see clusters of galaxies dotting the universe. It's not a uniform distribution of galaxies. They're clustered. And it's this turbulent history through which we are actually looking all the way back at the very pristine early light. That brings us to this decade. So this is the 3rd generation CMB satellite. It's called Planck. It's actually a European satellite. So I was also privileged to work on this experiment, and it measured the cosmic microwave background with extreme sensitivity and resolution. And it recently made this map. You can see the size of the team, there are 2 teams, and here's part of one team. This is what it takes to reach this level of precision and accuracy. It's a lot of people working together, and it is an example, I think, of the value of European cooperation, because all of these different countries came together to do this amazing experiment, get the data, and figure out something about our universe which is deeply profound. So Planck operates way out beyond the orbit of the moon, and it has exquisite instruments that can actually measure temperature variations from point to point on the sky of a millionth of a degree. And that's like if you are on Earth and there's a rabbit on the moon trying to measure the temperature of that rabbit. So this requires Planck's detectors to be cooled to 0.1 degrees above absolute zero. It's done with liquid helium. So obviously the mission has a finite lifetime because the helium eventually boils off into space and runs out. So that's what happened to Planck. But while it was cooled, it made this pristine map. I'm going to show you the level of improvement that we got basically once a decade. So that's COBE, and there's WMAP, and there's Planck. So there is this amazing increase in precision with which we can measure the parameters of our standard model of cosmology. So WMAP figured out the basic story, but now we can say things like this. The age of the universe, 13.82 plus or minus 0.05 billion years. That's sub% precision. So this sort of data is what is needed to try to answer one of the more audacious questions that we asked at the beginning of the talk. What is the origin of everything in the universe? So now I will move to that subject. So where did everything come from? Well, the precision of Planck allows us to rewind time back to, so this is a decimal point followed by 32 zeros and a 1, a tiny fraction of a second after the beginning of time. And at this time, we think that quantum fluctuations in something called a scalar field, we call it the inflaton, produced all of the structure we see in the universe, which got stretched out by the expansion of the universe, into everything that we see today. This is a really, really bizarre science fiction-like idea. Everything in the universe arose in tiny little quantum fluctuations. It was especially audacious till a couple of years ago, of course, when we didn't actually know, were there any scalar fields in nature at all? And then the Higgs field was discovered, so we know nature can do this. But the inflaton is a big extrapolation in physics. So the basic idea is that, there's this here be dragons regime at the dawn of time, t equals 0, we don't know what happened there, but it's very shortly after that, we think that all of this structure in the universe came from these quantum fluctuations. And then 380,000 years later, you see the imprint of those fluctuations in the cosmic microwave background, and then we have the story of the universe that I described earlier from that point on. So when you extrapolate physics this much, and you can't actually do an experiment to test it, which is probably a good thing, as I keep saying, it's a little bit, how do you figure out whether this is correct or not? It sounds so speculative. The virtue of this theory is that it makes very precise predictions for what you should see. I'll give you one example, again using the analogy of sound. So the information in these maps are hard to visualize or present in an intuitive way, but you can actually think about it as listening to a piece of music and trying to figure out whether the music has more power in the bass frequencies or the treble frequencies. Okay? So the very largest scales in the universe are the long wavelength or bass fluctuations, and the short scales are the treble fluctuations. And you can see, is there more power in the bass or the treble? Okay? And inflation makes a very detailed prediction for this. So imagine there was more power in the treble, then the universe would sound like this. Or if there was more power in the bass, it might sound like this. Or if it was nice and roughly balanced, it might sound like this. Thank you, Mr. Bach. And boo to Mr. Disney, because I usually use Star Wars music for this. I wasn't allowed to use it here. So the universe actually sounds roughly balanced, a little bit base heavy. And that's exactly what inflation predicts. So this bizarre theory was not the only theory. It wasn't the only culprit in town for what caused everything in the universe to come into being. There were other theories. There was cosmic strings. These are defects in space-time, one-dimensional, just stretched out across the whole of space. Or there are things called textures, which are like little swirls of space. These are things called phase transitions. You're actually very familiar with phase transitions if you have seen water turning into ice, for example. You know, something that can change phase. Space can do that too, and it can create structure. However, these theories also made very precise predictions for what you would see in the cosmic microwave background. And it's not like the data. So, you know, obviously many people worked on different kinds of theories for many years, sometimes entire careers, and then the data came in and told us the answer, and some of those theories were just wrong. Here I want to make a really important point, which is that looking and not finding is not the same as not looking. You can make theoretical predictions, but you have to test it with the data. And if the theory that you worked on is not the one that the data tells you is right, your time has not been wasted because you have learned something. You have learned that the universe works a certain kind of way and not another kind of way. That is extremely valuable information to the cosmological detectives. Now I want to move to the dark side of the universe. And again, you can see that there's a lot of dark stuff that we cannot see in the universe by looking at the cosmic microwave background. So basically, as these photons travel towards us from the very early universe, they're very slightly deflected by massive cosmological structures that they encounter on the way. This is called gravitational lensing. So just like a magnifying glass will focus rays of light are deflected by massive structures where gravity acts as a lens, not glass. And you can measure this effect using the precision of Planck's data. So you can see a very, very tiny difference, I hope, in these maps. That's what we're trying to measure. It's percent level changes in the map, in the shapes of these hot and cold spots that we see in the sky. And by inverting this effect, you can make a map of where all the matter is in the universe. This is integrated through 13 billion years of cosmic time, where all the stuff is. So when you look at this map, it doesn't look so interesting because it doesn't have all this intricate precision that you saw in Planck's map of the cosmic microwave background. This is like Kobe now. This is the start of a new field. It's a new window into the universe that allows us to map matter that is not visible. This is not the only evidence for dark matter, of course, but it is a strong piece of evidence. And that brings me back to the very, very bizarre fact that the universe is actually mostly stuff we cannot see. So visible matter, matter made of stuff like us, everything you test at the Large Hadron Collider, that's like 5% of the universe. 80% of the matter in the universe is dark matter. But matter is not the main part of the universe at all. It's dark energy. So it might sound like we don't know what we're talking about, and so we're calling things dark. You might be mostly correct, actually, if you say that. We have more idea about what dark matter could be than what dark energy could be. So dark matter, there are many extensions to the standard model of particle physics that might give us candidates, particles, that interact very weakly with normal matter and therefore very hard to detect but dominate the matter content of the universe. Dark energy is a different beast. I'm not going to really touch on it in this talk, but it forms the majority of the energy budget in the universe. And it's making the expansion of the universe accelerate. It's been doing that for 1 billion years. It's not going to stop. And it's going to lead to a very sad end to the universe many billion years from now. And we don't know what it is. We can measure its effect. We know what it's doing to the universe, but we do not have a physical understanding of that. So that's here be dragons. But we can learn a lot in coming years about dark matter. So I'm going to move to that. So how can we see dark matter? We can't actually see dark matter, right? We can see light. Why can we see light? We evolved to see light because the sun emits a lot of visible light. And similarly, stars, and therefore galaxies out in the universe, emit visible light. And so we can see them. We went and built instruments to measure that. And since the 1990s, we have been making massive maps of the universe in terms of the light from galaxies. This is part of the Sloan Digital Sky Survey. And this is not an animation. Each one of these galaxies is a real object placed into a big animation, and these are real galaxies. There's about 400,000 galaxies here. I could stare at this for hours. It's like a swarm of fireflies and flying through the night. And you can see they're clustered. They congregate. They're not scattered around space. Why do they congregate? It's because they're attracted to big filaments of dark matter that you can't actually see. So these 400,000 galaxies is a tiny fraction of the Sloan Digital Sky Survey. Other sky surveys I'm currently working on will map hundreds of millions of galaxies far out into the history of the universe. And in the 2020s, something called the Large Synoptic Survey Telescope will start. This is a 10-year survey of the entire universe. But so far, the pictures of the universe I've shown you are static. They're frozen in time. LSST will actually map what the sky looks like repeatedly every night, and we'll make a movie of the universe, of the changing universe. That's a window we have not had yet, and that is coming. So when you see these galaxies, it should perhaps remind you of seeing a picture of the Earth at night. Now, this is a simulation, which is, sensitizing to remember that. So for a very long time, before the invention of electricity, I guess, if you looked at the Earth at night from space, you wouldn't really know whether there were oceans, whether there were continents, etc. So now that we do have cities and we have electricity, you look at the Earth from space at night, and you can see the outline of the continents. You can see that there are land masses. And this is a biased measure, of course, of where the land is, because, you won't see Antarctica. You see where people live. Similarly, galaxies trace the underlying dark matter in some kind of biased way that we can simulate. Here is such a simulation, and again, you can see the utility of computers. This is a simulation of the formation of a cluster of galaxies. A cluster of galaxies is one of the biggest assemblages of stuff that you can see in the universe. Hundreds, thousands of galaxies. They're blowing out huge plumes of gas as they form. And eventually, these assemblages will start to look like objects that we can see in the universe. So how can we use this to test dark matter? So again, it's a little bit like how we figured out the standard model of cosmology. We have different models for what the dark matter particles should do, both in terms of interacting with each other, but also how they would affect the baryons, the gas, the stars, as these kinds of structures form. And as we get more and more precise maps of where galaxies live, what they look like, we can compare our models again with this data to figure out which of these theories are correct and which are not. And to do that, you need computers. So you might remember that when I showed you the Kobe detectives, there's a little funny desktop computer sitting behind them. You know, that's what I use. It's a supercomputer, and so you need hundreds of cores to run your very, very big computer codes, and you make very precise simulations of what the universe should look like. But on top of that, our data is now getting so big that we are starting to, for example, collaborate with companies like Google to actually extract information out of that data, because it's getting beyond the scale where a human being could sit there and spend a career looking at even a fraction of that data. So it is big data, and it needs big algorithms. So I showed you the universe in microwave light. I showed you the universe in visible light. And something that's starting to happen in cosmology now is looking at different wavelengths. So here you can see the universe in gamma rays, in X-rays, optical we saw. So you go longer and longer wavelengths, you eventually get to the radio, and we're starting to make surveys of the universe in all of these different frequencies. So here what you see is that there's a little kind of clip-out piece showing the galaxy again along the middle line. And you can see that there's different information at different wavelengths. And by looking at that different information, we can build a much more careful and complete picture of the universe. In the last part of my talk, I want to turn back to the origin of structure and how it relates to black holes, because everybody loves black holes, so do I. So remember this theory, this bizarre theory called inflation, where the universe created all of the structure in it via quantum fluctuations. This theory makes an extra prediction, which is that it should have set the whole universe ringing like a bell with gravitational waves. And there are many kinds of different types of evidence that we can seek as cosmology detectives. There is the absence of evidence, which rules out theories. There is circumstantial evidence. That's the sort of evidence that we could now start to think that inflation or dark matter are good ideas about how to describe the parts of the universe which are not described by standard models of physics. Then there's smoking guns. There's definitive proof. And if we could discover gravitational waves from the very early universe produced by inflation, that would be a primordial smoking gun. So that's very exciting. There's an avenue to find that, and that's because the cosmic microwave background is polarized. That means that the light that comprises the microwave background has a handedness to it. It vibrates preferentially in certain directions. The textures on these maps, which I love, it's like the Van Gogh color scheme, they actually try to give a hint of what this polarization would look like. And if there were gravitational waves in the primordial universe, that would imprint a faint signature into this polarization. Now, it's really, really difficult to observe. You have to do it from very cold, dry places on the planet, such as Antarctica. I have friends who winter over working at telescopes in Antarctica in the dark for so many months because they want to be the first to see this gravitational wave signature. So, till last year, and till this year for many of us, we didn't know whether the universe could make gravitational waves. And that's where black holes come in. So what you're seeing here, again, it's not an animation, it's not something anybody dreamed up in a computer game. This is a real simulation of two black holes spiraling together and merging. So what you see here is this red and green part. That's how time is slowed down near the potential wells of the black holes. The arrows are the swirls of space into the holes created by the deep gravitational wells of these black holes. It's going to slow down a little bit to show you the final merger of the event horizons of the two black holes into one. And this creates a sort of burst of gravitational waves called a chirp. And these gravitational waves then spiral out into the universe from the black holes, where a very lucky human being might actually detect them. So, this is the story, and of course, this happened. So, a pair of black holes, each about 30 times the mass of the sun, did this. They did it 1 billion years ago, about 1 billion light years away, and the universe vibrated. And so, we have seen the universe, we have heard the universe, but we can also feel the universe by measuring this. So as they merged, about 3 times the mass of the sun got turned into energy in a fraction of a second. That burst of gravitational waves arrived at the Earth on the 14th of September last year. And it made a tiny, tiny, tiny change in the position of a mirror in an observatory, which is one of the most amazing things that humans have ever built. This is a really amazing thing to have done. So these observatories, so you can see there are 2 of them. I'll explain a little bit why. So LIGO is a gravitational wave observatory, except that it was conceived a very long time ago, decades ago. It has been operating for 25 years or more. And till that time, it wasn't an observatory. It was an instrument for measuring noise. Can you imagine spending 40 years of your life measuring noise better and better and better and better and better, till you can detect waves crashing on the rocky beach, till you can detect the engines of airplanes flying overhead? You're measuring noise because you want to measure, for example, the gravitational waves emitted by those black holes, which will make a change in your mirror, in your laser interferometer, of a tiny fraction of the size of a proton. If that is not amazing, I don't know what is. This is like taking the full distance to the nearest star, which light takes about 4 years to reach, and over that distance, being able to measure the width of a human hair. That's what this instrument does. It is mind-boggling. And they measured this. They turned it on, and they were having an engineering run, and they saw this. Why are there 2? It's because, they're really, really subject to these noisy backgrounds that exist, things like the beach or the plains. I was even told at one point, although I haven't found any evidence for this, that they can, feel the alligators walking on the instrument in the Louisiana swamps, but maybe that's just a story. So they have 2 so that they can be sure that when they detect this amazing signature for the first time, they can see it happening in 2 different instruments, widely separated, and they can be sure that it is coming from out there rather than from your local environment. They go even further. These guys are really hardcore, you know. So there are 4 people in LIGO, and they will sometimes, without telling anyone, inject a false signal into the system. That's because they don't want to fool themselves. They don't want human beings to think they have detected something that is one of the biggest discoveries in human history and have that not be true. So they fool the other researchers into trying to analyze fake data. And they go all of the way to writing a paper and getting it ready for publication. And then they tell you, oh, no, that is not real. But this time, that system was not online. And there was one lucky human being. So this is a collaboration of hundreds of people. Some of the papers that have just come out have 1,500 people on them. But there was one lucky human being who is actually a very nice Italian researcher who works in Germany, not even in America, who was the first human being to see the signature of the dance of these black holes as they merged. That's an amazing thing to experience for the first time. But, you know, this is an amazing instrument, and it is just the beginning, because gravitational waves, now that they have been detected, and that is an amazing discovery, of course, can now be regularly detected, just as we have been measuring the universe through all of these electromagnetic wave bands. This is a new way of sensing the universe. And we can do it from space, and that makes us sensitive to different kinds of sources that could be detected. So you can have black holes merging of very different masses, ranging from solar mass-sized black holes to the monster black holes of millions times the mass of the sun, which are at the center of galaxies. And you can have dense spheres of nuclear matter, exotic matter, the size of London, spiraling in and create other signatures. Or, to tie it back to the origin story of the universe, if you wait for billions of years, you can start to see the signature of the cosmic background that's predicted by inflation. Of course, you can't see that in a laser interferometer. You would have to look for that in the cosmic microwave background. In the last couple of minutes, I want to show you that there's even more stuff that we don't know. And this again ties back to this idea of inflation. So inflation looks like it is the culprit for generating all the stuff in the universe. And if we measure these gravitational waves, we can confirm it. But if it's right, it makes a big universe. It doesn't just make the observable universe. It makes a universe much bigger than that. And even more bizarrely, that's not the end of it either. It will create structure on hugely large scales over the size of the observable universe, including other pocket universes. That is the implication of this theory. That is, it sounds like science fiction, and that is something that we have to figure out how to test if all of these clues keep falling in and pointing the finger at this theory. So, often, when one learns about scientific breakthroughs, you know, somebody's getting a Nobel Prize, everything is settled, everything is so certain by the time that that happens. I hope that hearing about these discoveries actually, you know, tells a better story of what science is like. There's a lot of lead time into making those experiments and making those discoveries. There can be decades, there can be careers spent working on theories which turn out not to be true. There's audacity in that, there's bravery in that. And it is a really important thing that we have these conceptions of this very long-term strategies between, making a prediction and getting the answer out. So, Einstein didn't actually believe in gravitational waves. He predicted them. This is the 100th anniversary of the discovery of general relativity by Einstein. He predicted it. He flip-flopped. He wrote a paper saying that gravitational waves did not exist. And luckily, the paper was not accepted because they do exist. But, so you can have doubts about what you're predicting. But the scientific process itself is self-correcting. So there are many blind alleys, and there are probably children in this room that can ask me questions about what I've talked about, and many times I have to say, the answer is I don't know. So, rather than being a collection of facts, this is a process in which we are exploring into the unknown, and by using the methods of detectives, we will hopefully continue to tell the story of the universe in more extreme regimes, further back in time and also into the distant future. Thank you.
Do gravitational waves take time, and how is that compatible with instant gravity between objects?